If we have vectors that are on different axes, we have to use something much more complicated. Let's say that we had a vector in this direction. Let's say the package, for example, was dropped off and the airplane was going 200 meters per second. So the package now has a velocity of 200 meters per second. Now let's say the package fell for a while and now the package is going 100 meters per second in this direction. How do we put these together? It's a much more complicated endeavor. When trying to add vectors that are in the x and y planes in different directions, x and the y planes, we have to use a little bit of a trick that includes some geometry and almost a little bit of trigonometry. So I'll show you guys how we do that, since many of you may not have had those experiences yet. So the first thing that we do is we redraw this same thing. And we're going to end up trying to make a triangle out of it. So how we're going to do that is we're going to say, well, where would this resultant line be? The resultant vector we're trying to draw is going to be right about here. So the best way to judge exactly where that is if we go 100 meters per second. Think of it like a map. We're first going to go 100 meters per second due south or straight down. Then 200 meters per second straight west or straight to the side. And that's going to take us right here to this point. That point is what we're concerned with, because that's going to tell us exactly where this vector is. So the best way to do that is we actually have to take this vector right here and just move it down and redraw it right here. Nothing has changed. We're still going 100 meters per second down and 200 to the right. But we need to redraw it here. 200 meters per second. Because now we have a triangle. And it turns out it's actually a right triangle. This is the symbol to show us it's a right triangle. This is a 90-degree angle. And so we have a right triangle here. And we know that with right triangles, we can use something called Pythagorean theorem. Pythagorean theorem, if you remember back to your math days, says that a squared plus b squared equals c squared. One of the short sides would be a, the other short side would be b, and the hypotenuse, or the longest side of the triangle, is always c. So if we square this side, we square this side, it would equal c squared. So let's go ahead and give that a shot. Right here we have 100, so 100 squared plus, right here we have 200, so 200 square that, and that's all going to be equal to c squared. If we square 100, we get 10,000. We square 200, we get 40,000. It's equal to c squared. Now if we add these two together to try and solve, we want to get c by itself, not c squared, but c by itself. We're going to end up with 50,000 is equal to c squared. Now we have to think back again. When we have c squared, how do we undo a squared? We need a square root. So take the square root of both sides to get c squared, turn it back into c, so we have c by itself. It turns out that the square root of 50,000 is 223.6. We're just going to say 224. So 224 meters per second again, because we're finding this vector. So we now know that this package is traveling at exactly 224 meters per second. Now comes the most challenging part. If you're trying to find out exactly what direction that's traveling at, you need to find this angle right here. How far from vertically down is it traveling? So we know exactly where that 224 meters per second is pointing. To do that, we're going to have to take another jump into trigonometry or geometry. So we're going to have to use something called, a little shortcut is called SOHCAHTOA. Now, SOHCAHTOA is just a shortcut to help us remember that if we have sine of an angle, it's equal to the opposite side of the angle over the hypotenuse. Alright? So these are the rest of the shortcuts. Sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent. So that means, for example, tangent of this angle would be equal to opposite from the angle would be this side right here, to adjacent, which means next to or near. That would be this side right here. So to solve this one, we're just going to use tangent. That's the easiest one to use. So the way you use tangent is you say tangent of the angle in question, the one we're trying to find, is equal to opposite over adjacent. So let's plug some numbers in. Don't forget we're trying to find this. We're trying to find the angle. So we need to plug in opposite, which is that 200 right there, over adjacent, which is going to be the side right next to the angle, 100. Don't forget, when we are dividing like this, we can cancel these zeros out because they're just placeholders. On the top and the bottom, they cancel out. We can cancel out meters per second. And all that we're going to be left with is tangent of the angle is equal to 2. You can see 2 right in here. So tangent of the angle is equal to 2. Now to get rid of that tangent, to get the angle by itself, is one of the trickiest things. It's a special little thing called inverse. We just take tangent to the -1. That's what happens when we subtract tangent from both sides. And we're going to be left with the angle is equal to tangent of 2. I know a lot of you aren't familiar with plugging things into your calculator like this, so here we have our calculator to show you exactly how to do it. We want tangent to the -1 of 2. That's all we got to plug in. So what you're going to do is look here and you find tangent. We have sine, cosine, and tangent here. If you look above tangent, you see a small blue tangent to the -1. So what you're going to do, if you want the small blue thing above the button, you push second. That tells the calculator, now we're going to do the blue one. Second, and then tangent, and then it's going to have a parenthesis there, and you're going to push 2, enter for equals. So if you do that, what you're going to find is the angle is equal to 63.4 degrees. 63.4 degrees. That means that this angle right here is 63.4 degrees. We now know exactly what angle that projectile is going at.